The title of my talk is on network systems. And one of the things that happened when I was at DOE was it's really learning from or drinking from the fire hose about the electricity grid. And so what I'm going to do is to share some of the lessons learned of our lessons learned and sort of the emerging trends that are going on in the electricity grid. And there are three networks that are getting coupled more and more: the electricity, natural gas, and the information network. And I mentioned in my title, Lessons Learned. There are actually few lessons learned because not much has happened. And what I'm going to talk about is what needs to happen so that we can get those lessons. So it's a slight change of title. Now, this infrastructure was claimed to be, by the National Academy of Engineering, the greatest engineering achievement of the 20th century. And it's true. I mean, everything sort of relies on this electricity infrastructure. You don't have electricity for a couple of days and, people get upset. And it is really the icon of any modern economy. And without electricity, it's called the second industrial revolution. And without electricity, really nothing runs. And in fact, the whole information network is based on electricity. But the key word out here is 20th century. And the question is, what's going to happen, what's likely to happen in the 21st century? Before I focus on the United States, I'm going to step back and look at the world and give you a picture of what the challenges and the opportunities are. This is the population density of the world. Okay, we are right over here somewhere, but this is the rest of the world. You can see where the people are. A lot of people out here, et cetera. And I'm going to overlay on top, and I hope you get to see this, the lighting of the world, which tells you where the electricity is flowing. And what you immediately see is that United States, we've got a lot of people, and it's bright. We need to make it brighter in a sustainable way. But there are many parts of the world where people have not yet turned on the lights, so to speak. And the question is, okay, how many are we talking about? So let me give you some numbers. Number one is there are 3 billion people out of 7 who have either no or very limited access to electricity. No is 1.5, and very limited access is another 1.5 or so. When I say limited access, is that they have the wires, but the power is not flowing. The electrons are there, but the power is not flowing. Okay? So it's 3 billion, almost half the world's population. By 2050, additional 2 billion people will be added to the same regions that this is going on. Okay? And it'll be about half. So the population growth is faster than the electrification in some places. Number 3, there are massive levels of urbanization that are going on as we speak, and the demands on the electricity infrastructure is huge and can't keep up with the demand. And finally, the question that we're trying to answer is that we have an electricity infrastructure which, compared to the rest of the world, seems really good. So the question is, how can we modernize the infrastructure? And the second question is, how can we provide access to affordable electricity to every human being? I consider this to be a human right. Because if you do not have electricity, you do not get into the modern economy. Okay? And you're stuck in a certain stratum of income levels, et cetera. There is no economic growth. So these are the big questions that we're trying to answer. And the question is, why are we trying to modernize infrastructure? Is it for, just to modernize? Or is there a need for it? And I'm going to sort of give you what that need is. So my talk is outlined in 3 topics. One is, what is the current paradigm of electricity infrastructure? Secondly, what are the emerging trends? And finally, what is the shifting paradigm? And we're living through that. And it's, as opposed to, computer science, which happens very quickly, seemingly, at least, to the public, this takes time. And it's going to take time. So what is that current paradigm? The current paradigm is the following. Our electricity grid looks like this. This is the current architecture. You have a centralized big power station, mostly thermal power plants. You generate a lot of power. You take it long distance at high voltages through transmission lines. And you need high voltages because you want the currents to be low and thereby the losses to be low. That's where the high voltage is. And then it comes to local distribution networks. And you have a distribution substation where you drop the voltage. And then you get these feeder lines near your neighborhood, which is like 13 kilovolts that are running. And then from those, you have transformers, which give you 240 volts, out of which you take half of it, you get 120 volts in your home. That's the architecture. That's the paradigm that we're living in. And it turns out that this architecture goes back to Tesla and Edison. The architecture has not changed. The devices may have changed. But this construct has not really changed. And it is based on, again, the centralized generation, one-way power flow to zillions of load. Why centralized generation? Because these are all thermal power plants. And in thermal power plants, the economies of scale suggest that bigger is better. And that's why you have 1 gigawatt plants of coal-fired power plants or nuclear power plants, et cetera. Okay? So that's been the paradigm, and really this has not changed. So what have we, so it turns out that because of this technological paradigm, our institutions have been framed around it. Our legal framework, regulatory framework has been framed around this paradigm. So everything and the business models goes along with it. So the technology is sort of the key out here. And I'll talk a little bit about the institutions because these are all coupled together. So what have we done? Well, this is what we have built up. This is the high voltage transmission network in the United States. And these are at different voltages. And for really long distance, you need the really high voltages. In the United States, it goes up to 765 kilovolts. In China now, they have 1 million volts, both AC and DC. And they're ahead. So in terms of, what have we done to this infrastructure in terms of information? What is this smart grid all about? Well, let me sort of dispel some myths out here. So what have we done? If you look at the transmission network, we have put this. These are called phasor measurement units. We have about 1,000 in the United States. And this is what it looks like. It looks at data. And this is what happens. These are PMUs. It measures the current. It measures the frequency. Okay, we are all at 60 hertz, but it's not exactly 60 hertz. It measures the time. There's a timestamp. There's a voltage. There's a location. There's a relative phase angle. And it samples every 30 milliseconds, and it sends out data. And you're getting petascales of data now. Okay, that's what's going on. Of course, there's communication. This data needs to be communicated. And frankly, we have relatively advanced communication with this and with security built into this in terms of improved communication for these units. And finally, what we have not done well is the computing part of it. What do you do with the data? And I'll come back to that later on. Again, this is for the high voltage transmission network. That's only part of the system. It doesn't talk about the distribution network. So we have put these units in this middle of the network at the high voltage part. What else have we done? Question,
when you say you put them in the network, do these measuring devices have to be connected?
They have to be connected, absolutely. The Hall sensors and all that, they have to sort of measure what the current is flowing. They're magnetically coupled. But yeah, that's right. Okay. Right? So that's what's going on. Now, the other side, this is in the middle of the network. And now I'll talk about the edge of the network. This is what we have, smart meters. Okay? And these are right at this point out here. And you can measure, the current and voltage and power. And there's been a wide deployment. In fact, both the PMU, the phasor measurement units, as well as the smart meters, a lot of that was deployed using the stimulus. The 1,000 PMUs as well as the smart meters, that was part of the effort, is to get some numbers, get some data out of it, which is actually a good thing. And if you look at the deployment, we have about 50 plus million smart meters out there. This is quite a bit. And they're sending data every 10 minutes, 15 minutes or so. Okay? So that's all we have done, really. What is missing, largely missing, is what's the data in between, the distribution network. In fact, many of the utilities don't even know where the wires are. That's the state of the art. And they still pump power in one end. the power comes out of the other end, but there's no idea what happens in between. Okay? So that is where we are. So question really is, what can or should we do with the data? There are lots of data out there. And what is going on right now to some extent is diagnostics. It'll be great to have situational awareness. We don't have for the full grid, but we have for little bits and pieces. Monitoring outages, failures, and billing. The smart meters are great for billing. You don't have to send someone out there to read the wheel going round and round anymore, at least in those 50 million ones. It saves money. What we have not done, and so this is what is going on, we still don't have full situational awareness of the whole grid in the United States, which is broken up into pieces, and I'll come to that. But that's what, that would be great. The second thing is operations in real time. And that means load and generational control, system optimization, which, by the way, for the grid, for this mesh network, if you're trying to pump in power and you want to maintain voltage, the optimal power flow is an NP-hard problem. And we still, this is not done. This is done in a very rudimentary way. And the resilience against threats during operation. We're not using the data to do that today. And finally, for planning, it's very important. As I show you, we need some upgrades in our grid. And how you do that in terms of capital outlay for a utility, extremely important for financing. And we need the data as to prioritize. We need to replace this particular substation transformer as opposed to that one because this is looking bad. And that data is very, very important in terms of capital outlay for this. So this is what we should be doing, and so far this is widely open right now. But to understand this, you really have to understand how the grid operates today so that we can appreciate what really needs to be done. And this is where the technology and the institutions and the regulatory framework all meet together because they have to operate under certain rules and laws, et cetera. So I'm going to give you an idea of how that actually works. So the first thing is that there's the wholesale electricity. And this is electricity networks or electricity grid really 101. Okay, and there's much more details. I'll just skim on the top to give you an idea. I'm choosing California as a canonical case. You have what I call the California Independent System Operator. They run the grid. They're based in Folsom, California, just east of Sacramento. And what they do is to do wholesale high voltage transmission, bulk electricity handling. They're the guys who balance the grid. It is not PG&E. It is these guys who balance the grid. And what they do, and by the way, because sometimes somewhere they cross state lines and they deal with Nevada and Oregon, et cetera, and Arizona, they follow the federal rules, the Federal Energy Regulatory Commission, and they follow the NERC rules, which is the technical arm of FERC, roughly. So this is the grid operator which balances the grid. And this is load and generation is balanced in real time. Now what they do is to buy electricity from solar plants, from wind plants, from nuclear plants, natural gas plants, et cetera, or from utilities who run those plants. They can be independent plant operators, or they can be utilities who run the plants, like PG&E, Southern California Edison, San Diego Gas and Electric, Sacramento Municipality, et cetera. And these units can buy and sell. These units sell. And what they do is to have an auction every day, a stock market. And I'll come to that in a minute. But these have regions, like PG&E is this white region out here, Southern California Edison over here. These are monopolies out there. And they have to be regulated because they're monopolies. And so that's why these units come under what are called the state, because they remain inside the state and they're governed by state rules. And these units then give you the retail market because PG&E sells us electricity at home, to our buildings out here, to factories in the local region, in this white region out here. So they are not balancing the grid. They're selling and buying from the wholesale market. Okay? So that's how it works. And this is California Utility Commission, Public Utility Commission. These are the federal rules. And this is the wholesale market. These are the retail market, et cetera. So how does the wholesale market work? Well, it's done by a market bidding process. So this is, you have the wholesale, the California ISO, and people have to bid. For example, I bid today. Most of the electricity, by the way, that is coming today was planned out yesterday. It's not a real-time market. So they have to estimate the load, and then they dispatch generation. So yesterday's generation, and let me just show you, it's like a big knob. So most of the generation, let's say in this case, this is New England ISO, it's 13 gigawatts was dispatched yesterday. And that was already planned. And it's done by bidding process. For example, if I offer $20 a megawatt hour, and someone offers $30 a megawatt hour, my 100 megawatt goes first, and then someone else's 50 megawatts goes second. So it's a bidding process in a market. So this is called the day-ahead market. So they're bidding in the day ahead. So today's bidding happens for tomorrow. Then they don't get exactly right. The estimates are not quite right. And so they go in an hour-ahead market. So they correct it within an hour. Then they have a 10-minute market, 5-minute market, et cetera. And then they have a second market, which is called the frequency regulation market. Okay? So this is trading going on. And in fact, if you go to Folsom, it'll look like this. And they're looking at the whole California grid and monitoring the frequencies, voltages, et cetera. Now, to really appreciate this, it is important to understand all the timescales involved. So this is now, you have a millisecond. 16 milliseconds, very important because that's 60 hertz. Okay, one cycle. You have 1 second, 1 minute, 1 hour, 1 day, 1 year, 10 years, et cetera. That's the whole time scale. On the one hand, you have asset planning. That is, you got to plan 10 years ahead or 20 years ahead. And here you have faults because you can have circuit breakers have a fault which can happen below a cycle. And in between, you have all kinds of controls. So this is where the day-ahead market is. You have the hour-ahead, 5-minute frequency regulation, et cetera. So let me tell you how this actually works. Yes?
Question. This might be a silly question, but it sounds impossible. You're buying my electrons, but how do I get them delivered to you through this?
So you offer up, so I bid, and then you say, okay, I have,
I know you get my electrons and not somebody else.
Oh, you don't know. Oh. But I put my power into a mesh network, which is the transmission grid, and the electrons flow according to watered down. There are no routers.
That's what I was.
There are absolutely no routers.
Okay.
There's actually one router in New York area. It's extremely expensive. So one of the things we did in RPE, can we build cheap routers for electricity? So it's a mesh network. It goes down following Kirchhoff's law. Okay, and you just dump your power onto the system. The only thing you got to do is to maintain voltage at the other end. And so, sending in power to maintain voltage at these nodes, that's the problem. If you want to do it optimally to minimize cost, that's an NP-hard problem. Okay?
What is the voltage drop between the power plant? I mean, there's many transformers in between.
That's right. Most of the voltage drop is in the transformers. The losses, total losses, it's about 5 to 6% or so. Someone may have a better number, but it's roughly that. Yeah. So how is this done? Most of it is actually happening in load estimation. So we estimate load in many ways. This is the day-ahead prediction based on history, weather, etc. Okay? This is where a lot of machine learning could actually help, by the way. Then you don't get it exactly right, and then you have the hour-ahead estimate. And then you have 60 hertz based estimate. And what is that? That's the frequency regulation. That is the frequency, the 60 hertz. Frequency is a proxy for a mismatch between load and generation. That means if I have too much load, my turbo machinery is going to go slow. And so if it's going at 59 hertz, that means I have too much load, some generation has to be pumped up. Okay, and if it's going at 61 hertz, then there's less load, I can cut down generation. So that's the frequency regulation market. And by the way, in the United States, it is 60 hertz plus minus 0.035 hertz. That's the regulation that they have to do. So this is, again, this is all about load estimation. And what they do is to dispatch the generation accordingly for what the load is. So you have a day ahead, 95% of the generation is dispatched day ahead today. And so you can see, as I was saying, 300 megawatts is $60 a megawatt hour. That'll go first, and then 400 megawatts is $75 a megawatt. This is part of the bidding process. Okay? And then about 4% goes in our head, about 1% goes in the 60 hertz base market. And that's how the grid is operated. The generation always follows the load. So that when you turn on a switch out here to turn on the lights, some generator, you don't have to worry about controlling the load. Some generator is pumping up so that you get your electrons, you get your power out here. That's how it works. That's the paradigm, the Tesla Edison paradigm. Just to give you some data, here is a day, about a year ago. This is typically, it happens every day. This is from Cal ISO. This is actual data. This was the day ahead forecast out here. This is 23 gigawatts, 24, 25, 26. So each is 1 gigawatt of power. So you have the day ahead market, and that was not exactly correct in terms of prediction. This is the hour ahead forecast, and this is the actual demand. And the difference at any given point can be about 2 gigawatts. Okay? So that's how the load curve looks like for California. And I'll come back to that. There's some very important implications that are going on right now. And here is the renewables part, for example. This is solar. This is geothermal and hydro, and this is the wind. People think that solar is unpredictable. It's actually quite predictable. You know when the sun's going to rise. You know when it's going to set. And you generally put your solar plants not in San Francisco where it's foggy, but somewhere in the desert where it's always sunny, right? The problem is the wind is not quite predictable. So that is now on the wholesale, in the transmission network, in the wholesale market. And by the way, that determines the price out here. The question is, what happens in the retail market? Well, these people buy the electricity. PG&E buys the electricity and sells you the electricity at home. How is that pricing done? It is done in a very dumb manner, frankly. It is a tier structure mostly. So at home, you may be paying 13 cents a kilowatt hour for a certain amount of kilowatt hours spent over a month. And then if you exceed that, it goes to 15. And if you exceed that, it goes to tier 3, which is 32 cents a kilowatt hour. And you have no transparency as to when that happens. You're doubling the rate of electricity that you're paying. And this is what's going on today. And there is really little correlation between the dynamic price changes out here because of a market and the pricing out here. And what you really want and design, this is where the Public Utility Commission comes in, they design these rates in such a way that you may have the wholesale prices may exceed the retail price once in a while, but not on an average. And this difference is the margin where the utility is making money. And when these wholesale prices go up out here, they have to buy high and sell low, which is what happened during the big energy electricity crisis in California because of Enron. Because they were cooking up things where the wholesale price would go up, and then the utilities are toast. And that's why, so this is how the whole pricing and the technology works. So let me show you some emerging trends that are happening, which are worth noting. Number one is natural gas is going to be hugely important for United States because we have a lot of natural gas and it's cheap. It's the cheapest way to produce electricity today. In the wholesale price, it's about 5 cents a kilowatt hour. So all the capacity buildup that happened, for example, in 2013, mostly was natural gas, solar, etc. And there was even some coal out there at that time. Today, there'll be zero coal. And so what you're finding is a shift between, so yellow is natural gas, blue is coal, and you're finding that coal is being substituted by natural gas mostly because of economics, and to some extent because of what the regulations could be in the future. And so this huge transition, which is very rare, this faster transition, by the way, in the electricity network, this is going on. And what that is bringing on is a coupling between two networks now, which is now the electricity infrastructure, the network out here, and the natural gas network. And when you have the coupling between the two, some interesting things happen. And they're happening today. So I will now imagine you're in New England. In Boston, it's hard to imagine when you're in California. But just imagine you're there and you got the polar vortex. What happens then? You need to heat your home, and heating is mostly by natural gas. So you're finding that you got to turn on the crank on the natural gas and you're sucking in more. Now, what's going on then in the rest of the network is the following. Because you do not have enough pipelines in the New England area, the throughput of natural gas is not enough. So the demand is high, supply is not enough, and the price of natural gas shoots up. And these are spikes about 5 to 6 times the average price. This is natural gas, dollars per million BTU. Ignore the units for the time being. It goes from an average about $5 to, in this case, almost $20. I heard that in the Pennsylvania area, in one cold day, it went up to about $120. Okay? So these are the spot prices going up. Now, because your electricity generation is dependent on natural gas more and more, the electricity prices shoot up. So you find this very nice correlation between the natural gas prices and the electricity prices. So if I'm a consumer, I got a double whammy now. Because my natural gas price goes up, my electricity price goes up, and I'm paying double in both of them. So there is no way today to decouple them because of the fact that we are over-reliant on this. Should you be storing natural gas, or should you have a generator at the end so that you can generate electricity with your heating? No one really has a solution for this today. So that's one trend that's going on in the coupling. The other is weather. And I want to show you, we all understand global warming. The world has warmed by 1.3 degrees Celsius from the beginning of the Industrial Revolution. Well, that's the average. Let me show you the distribution. And this is the distribution of temperatures during summer on land in the Northern Hemisphere. Okay, this is where we live. And what it'll show you is, some summers are hot, some summers are cold. So you'll see that this is the theory. This is the distribution, this is the theory. These are hot summers, these are cold summers. This is deviation from the mean. And what you find, this is actual data. And what you find is surely the average has moved. The things are getting hotter. 2014 was the hottest year. But that's only part of the story. You find that the tails of the distribution are reaching 4 to 5 times the standard deviation, which it had never reached before. And the tails of the distribution have a disproportionate effect on the infrastructure. Because when it gets hot, you turn on the air conditioner, and the whole system is loaded. And this is a really important problem because the outages, and not necessarily in California, but the rest of the country, go up when you have this kind of demand. So this is one trend that is going on. The second trend is age and security. This is a typical transformer in a distribution transformer that goes from the high voltage transmission to a medium voltage in a distribution network. And it turns out they are installed around the world, around the country. We have about $1 trillion of assets in the United States on the grid. These are some of them. The life expectancy of these transformers is 40 years. Okay? That's the life expectancy. The average age in the United States today is 42 years. So we are at -2. I mean, think about it. This is a fundamental infrastructure. All our information networks all depend on this, and this is the state we are in. In terms of security, let me give you just one anecdote. And here is the Highway 101, PG&E. There's a big substation out here. This is Morgan Hill. This is San Jose. You're all familiar with this. And you've seen this transformer, the substation, I'm sure. It turns out that in April 16th, about 2 a.m., there were people with guns who shot at the radiators of the transformer because they have cooling oil running to maintain the temperature. They shot at that so that the 50,000 gallons of cooling oil were leaked, and they tripped the transformers. But 15 minutes before that, the fiber optic and telephone cables were essentially sheared off so that 911 was disabled. And for about a year, no one heard about it. We were following this closely, but no one heard about it because it happened the same night of the Boston Marathon bombing. And we still haven't caught these guys. And this is just a cyber-physical threat. This is not just cyber threat. In terms of cyber threat, when I was in Washington, Department of Energy, my first security briefing that I got, in a classified briefing, and I looked at the data of what was happening on the grid and what other nations were sort of meddling around. And my first reaction was, I hope, this is a visceral reaction, I hope we are doing the same thing to them. Probably not the right reaction, but that was it was pretty bad. And so that's going on. We are being mapped out. So this is another trend, unfortunate trend that is happening. The third one is economic. And that is the fact that, and climate-wise, it's also another trend. Yep?
So what were the repercussions of people shooting up that substation?
We haven't caught these guys.
Well,
the repercussions. It turns out we were lucky that that particular substation could be avoided and the electricity could be routed through other substations so that people didn't get the full brunt of this thing. So it could be a trial run. People were trying out, but it happened. So the other aspect of this is the emergence of renewable electricity and as an economic issue. So this is wind electricity. The cost of electricity from the wind is coming down. It's in fact come down and flattened a little bit. And this is in comparison to others, and this is, by the way, the adoption of wind electricity is going up exponentially. And it is almost at the same price or cost in production as wholesale natural gas electricity cost. And it's cheaper than coal today. The same thing is happening in solar. So while wind is centralized, but it's intermittent, solar is both intermittent and distributed. And I'll come to that. It could be at the edge of the network as opposed to in the middle of the network. And this is in a utility scale solar. This is commercial scale. This is residential scale. And this is coming out at a rate that we never predicted. In fact, when Steve Chu and I were in the Department of Energy, we launched something called the Sunshot Initiative to get the cost of solar electricity down to 5 cents a kilowatt hour without subsidies, so that it'll be the cheapest way to produce electricity. And in fact, we might reach that before 2020. And this is comparable. The wholesale one is getting comparable to the natural gas cost, which is the benchmark. And the retail one, the rooftop solar, is actually getting comparable as well to the retail electricity, which is where it's relevant. So this is happening. In fact, by 2020, we're going to see this to be cheaper than many other places. And I'll come to that in the paradigm as well. This is already happening in California to the extent that it could affect the grid. As I said, this is the California load curve. This is about noon, and then it flattens out. When people go home, the load goes up and then comes down again. And what is happening today, and it's going to happen in the future because of what's happening at the edges of the network, is the following. This load is going to go down and then shoot up to the point that this is called the duck curve, because this is the duck's belly, and the duck is getting fatter. And you have a ramp up of about 150 to 200 megawatts a minute between 4 o'clock and 6 o'clock or so. So the question is, why is this happening? The reason this is happening is because of rooftop solar. It's a negative load. And the way it is being deployed, we don't know exactly where those are. So we don't know where the negative load is coming up. And the wholesale market has this excess electricity, so the way they're trying to handle this is to do negative pricing. That is, they'll give you money to take the electricity away because they have excess electricity. So this lack of coordination is a big deal, which is, I think, where information could come in and actually optimize the system. So another trend that is happening is storage. This is lithium-ion battery costs coming down and comparable to getting to lead-acid batteries on a first cost basis, and on a cycle basis, it's even cheaper. And there are other batteries that we funded from RPE that are getting competitive as well. So storage is getting cheaper. So if you now put all that together, this is the current paradigm we have. You have a wholesale ISO, which is, let's say I'm taking a number, selling electricity to the electric utility at about 7 cents a kilowatt hour, plus minus fluctuation based on market. Let's say we assume that. And that utility, like PG&E, is selling you electricity at 15 cents a kilowatt hour. Okay? This is the market structure. This is the tier structure. You hope that the wholesale price is lower than the retail price, and the utility doesn't go out of business. And that's the paradigm of the one-way power flow. This is what could happen based on the trends that we are seeing. You have this same thing going on out here, 7 cents plus minus delta based on the market's fluctuation. And this may still be 15 cents a kilowatt hour. But you may be able to, in the near future, generate electricity from your rooftop at 10 cents a kilowatt hour, which is cheaper than the retail. What would you do then? Well, you said, I don't want the retail for the time being when the sun is up there. You may have storage to store that electricity in various forms. Or if you have a gas line coming to your home, which most people do, you may like to generate electricity from that and use the waste heat to heat up your water. This is called combined heat and power. In which case, this may actually be even cheaper than the solar. So now you have this home. It's just like, if you went 30 years ago, you had only the telephone line and the antenna on your TV to get you information. Now you have so many other ways to get you information and you can switch. Well, the same thing could be happening in the power sector as well. So that now that architecture that I drew up in terms of the centralized generation, well, you may have some centralized storage. This centralized base load need not be just base load, it could be intermittent as well. And you have storage, and you have generation and storage at the edges of the network itself. Now, how do you manage this, and what's the new paradigm that we should be using? And what I'll tell you is this is what's going on. This is the first time in the history that the distributed and intermittent is actually getting cheaper than the centralized base load, and in the history of the electricity grid. So the past 100 years, where centralized baseload generation follows distributed variable load. In the future, we may have centralized baseload plus intermittent generation plus distributed generation, storage, and load, which is the producer and consumer, prosumer. So who leads? Who follows? And who pays? We don't know that. We had wholesale price always lower than the retail price so that the utility makes margin. We don't know what's going to be because the cost of distributed generation could be lower than the retail price. Isn't this an instability? Probably is. And a lot of utilities are worried about this. And finally, the consumer has a single option in the past, and we may have multiple options. How consumer has multiple options for electricity, how does he or she minimize the cost? How does system balance with two-way power flow? We still have not quite worked it out. So the real issues in terms of the renewables is that how do we integrate high penetration of renewables? California has a mandate now called the Renewable Portfolio Standard. We want to get to 33% renewables by 2020. Now, if you have that, that's a pretty high penetration. Then how do we manage the centralized intermittent and the distributed intermittent resources? We still don't have any idea. And what is the problem is in the dispatch models. In the dispatch, we are dispatching 95% of the generation a day ahead. Well, it's very hard to predict wind power exactly in a day ahead. So what needs to happen is to transition this to something like 70% out here, 25%, 5% out here, so that you have 30% out here. You may expect to get 35% wind, for example, integrated. The question is, how do we do that? And the ISO has not quite figured this out in terms of control and optimization of the system. We are going to see more of load following the generation, which is a new paradigm. The generation always followed the load, but now the load has to follow the generation, which is much cheaper because you can then control if your solar light is going down, maybe you can dim the lights just a little bit. Today, we do that only for managing peaks, but it has to be done in a dynamic way, which means the load need to know when the generation is coming down. So information and communication has to happen, and someone needs to compute that. So the most cost-effective options that a lot of us see is that if you want penetration up to 20 to 25%, don't put storage, because storage is expensive. What you really want to do is the dispatch operation needs to be changed and more towards the 15-minute market, which means you have to control, increase or decrease the load to follow the generation, and maybe put new transmission lines so that you have a wider area to balance the grid. If you want to go higher than that, then you want to put storage and other turbines, et cetera, to balance out the intermittency. A lot of people are asking the question, what about microgrids? What are microgrids? Because our grid is just one network. Well, the microgrid, let me explain what people mean by that. You can take today's grid, which is high voltage generation, so high voltage transmission, then a distribution network, and you have a feeder lines in homes. You could imagine this to be a microgrid out here. If you could connect with the grid, legacy grid, or disconnect with the legacy grid, you can assume these to be microgrids. These could be independent, disconnected, could be connected as well. And this actually can take this unit out here and maybe this out here, and you can form a microgrid. And there's a lot of people are proposing that as a new way of handling these issues. So how do you connect and disconnect when necessary? Now, when you disconnect, here there's a problem. Because today you don't have to worry about frequency. Your 60 hertz is managed by your independent system operator. When you disconnect, your appliances still want to run on 60 hertz. Someone has to regulate it. Someone needs to regulate your voltage to be 120 volts, which is regulated by your grid today. So when you disconnect, you have to get automated and then automate load generation balancing, as well as voltage and frequency regulation when disconnect. And then can this unit connect with the grid and provide the services to the rest of the grid so as to eliminate some of the problems like the duck curve for the rest of the system. So that's a proposal out there. And it's not, it's not sure, it's not clear. The jury is still out whether that's the right way to do it. But if you are to do it, here is an idea of how that could be operated. And this is just a proposal at the time.
So question,
Yeah.
Does Stanford work like a microgrid? Because I understand that we have our own generation capacity.
I don't know Stanford. I'm here only 6 months, so I still have to figure this out.
Because there is a power generation
That's right.
facility here.
But I think we may be buying power from Palo Alto. I don't know. Others may know out here.
There's also gas-based generation here.
Okay.
Yeah. Okay, that's fine.
In fact, we could, if this is indeed a microgrid, we could try some experiments out here as long as no one brings the grid down
My
out here.
understanding is, yes, that Stanford sort of buys electricity, it sells electricity.
Okay.
Over time.
It acts like a municipality then.
Yeah.
Municipalities actually, Sacramento, for example, is a municipality. They're buying electricity and they manage the pricing. It's not the PUC. And in fact, it's much more progressive in that sense, the municipalities. I think Palo Alto is one. So how do you manage centralized, distributed, which is at the edge of the network, like rooftop solar or storage, and loads, and intermittent, which could be both distributed and centralized in a system operation? And that's what we are getting into in the next decade or so. And we really don't have any idea. So here's a proposal. So you have a legacy grid, you have generation, but now you may have generation at the edge of the network. You have load at the edge of the network, you may have storage too, if it gets really dirt cheap. If the Gigafactory and Tesla is that successful, it'll get really cheap. So you may have this. Now, how do you manage this whole operation? So one is to really make some units, like collapse them together into a load generating units into a microgrid, and then sell that to the grid in an aggregated way. That's what utilities do, they're aggregators. But you can aggregate in many different ways. And a microgrid is one of them. Well, you may want to have, and this is a technology that is coming on right now, is electronic power conversion. This is going down and going up in voltage using electronics, which is Juan Rivas and others are doing it out here. And when we were in Department of Energy, we felt that this was very important. We put like $100 million of funding into new kinds of semiconductors, et cetera, to do the electronic power conversion and get it cheaper and cheaper. Why is this important? Because then it's not only the inversion of power from DC to AC, but you can control phase angle, you can actually do control of voltage regulation, frequency regulation using an electronic platform. And so this, I think, is very, very important. And it's not just power conversion, it's switching. In fact, imagine semiconductor-based circuit breakers and on monitoring. You can measure the power. So imagine you have these at certain nodes. This could be expensive, so imagine this to be only a few, depending on what the cost is. And imagine if these electronic power conversion also has a network computing platform built in. So you can send signals for optimization. Now you got a distributed computing platform, you got all these power power conversion and power management devices distributed now. Now the question is, how would you compute? How would you isolate? How would you disconnect? Remember, I told you that when you disconnect, you got to regulate your frequency, and that has to be in real time. And you need stability of the grid in real time at the 16 millisecond time scale, because that's a cycle. So you may have this, you may call a microgrid, which you can connect to the grid and disconnect, provide services. Or you can have another microgrid out here, and you can have an array of microgrids. So you're essentially packaging. Now, it's very important that if you are to create microgrids, that there is no, when you isolate yourself, there is no system operator. It has to manage itself. It has to be fully automated. And so local autonomous estimation and optimal dispatch of load generation and storage has to happen. And that needs algorithms, that needs that needs distributed algorithms so that you're not prone to threats because of a single unit, a single point of failure, et cetera. So these have to be developed. Okay, some of it has been, the control units have been, but full system optimization, well, I think that Stephen Boyd and others are working on it. But that needs to come together. And then, of course, where do you use the cloud? People say cloud computing. Well, the cloud is very powerful, but you do have network latencies. And if you rely on the cloud completely, then you have a problem because you have latency. This has to be done in 16 milliseconds. So networking speeds become very important now, or 16 milliseconds or less because you want to prevent faults. So you want to use the cloud to collect the data, to have optimization signals going into these units to optimize and minimize the cost, but you don't want to rely completely on stability of a grid on the cloud because of latency issues. You have to have autonomous units embedded in this. You can think of this as the Internet of Things, if you may, but that's what you really need, and that'll create some value. So this is a huge problem that needs to be resolved, and it's not completely resolved yet. These are just proposals right now. But what is likely to happen is the following. You have the electricity network which distributes power, which is geographically distributed. You have a gas network, which is molecules, which is geographically distributed. That's getting coupled. And you have the information network, which is sending out bits. And there's dynamics out here. There's latency, there's delays that happen out here. There's coupling out here as well. And the dynamics of the whole system, it's not digital, it's analog. Because things are turning up, and now you may have voltage spikes going up, and those all need to be managed. That's an analog problem. And there are big questions out here. Number one is, how can we design a resilient coupled networks while minimizing the cost? I don't think this has been worked out yet. How can we understand and control system dynamics from the sub-cycle to seasonal timescales in these coupled networks? Not clear. And finally, how can we prevent catastrophic failure? And catastrophic failure, let me give you an example of this. This is what happened in India for 2 days in 2012, where the whole northern part of the grid just completely collapsed. And 620 million people, 9% of the world people, that lost electricity, just came to a standstill. And it turns out it happened because of something called the cascading failure. It was hot summer. People were drawing a lot of current in agricultural pumps. Pumps produce reactive power as opposed to real power. They need reactive power. And then the phase angle between the voltage and current sort of shifted. And in India, they didn't have controls on those. And you're drawing more current. Suddenly, one circuit breaker trips. And if one trips, all the load or the power is shifted to the rest of the network. And then another one trips. And then you have a cascading failure. And this happened, by the way, in 2011 in San Diego, the same issue. Okay? When one failure happened, then it cascaded. The same thing happened in 2003 in New York area. It's a very similar problem. The lessons learned were minimal, frankly. We don't know how to stop cascading failure. So what we don't know, even in today's network, only electricity network, without the information and natural gas, is that how close are we to a phase transition like that? Okay, can we predict it? Can we stop it before it happens? Can we move away from it? And there are some telltale signals like frequency fluctuation. But can we get insights into that before so that we can prevent these failures to happen? And that's still a wide open area.
Running a little short on
Yeah, this is my last slide. So this is now, we have these sensors. It's time to create some value. And the value is created not just in diagnostic, but in operations and planning, et cetera. So let me stop here. Thank you very much.
There's a couple of short questions or clarifications. Let's back there.
It seems like you mentioned the curve where there's a depression in the middle of the day. There's the,
Yep.
the load
The duck curve.
much lower, and then the sudden spike.
Yep.
in the afternoon. It seems like you still need a grid infrastructure that provides for the peak. So therefore, if you don't get some kind of edge storage, you still have the same problems. You just for a briefer period of time of the day.
That's right. That's absolutely right. In fact, the reason I showed this temperature going to really hot extremes is because today you got to design the grid for the extreme, which is very expensive. And storage would certainly help, but storage is also expensive. And I think the cheapest way to do it is to control load, follow generation when you need to. And that means the loads need to know what the generation is doing. The generation needs to know what the load is doing. And that means measurement, that is data, communication, and some level of computing so that they are coordinated. And that is not there today.
Let's take one last question.
Yeah. What's the impact of getting rid of daylight saving time?
Oh boy, that is never quite thought of that.
Because right
Yeah.
now it increases the air conditioning load a lot.
Yeah, I don't know that. I don't know the answer to that. And frankly, I think given this, the duck curve that I talked about is really due to solar. And if you change it by 1 hour, it happens to, yeah, actually that's a good question. I don't know.